So, welcome to the next session. Now we are going to see about the MMF method and the ZPF method of voltage regulation. So, myself P.L. Somasundaram, assistant professor from the Department of EEE, belongs to M. Kumarasamy College of Engineering. Let us enter into the session. So in the last session we have discussed about the EMF method. Now I am going to explain you the MMF method. So first, what is the difference between the EMF method and the MMF method? EMF, electromotive force, from the open circuit voltage and the short circuit current, we have calculated the synchronous impedance ZS. By using that ZS, we have calculated the XS. XS is nothing but X suffix S is the synchronous reactance. So by using that synchronous reactance, we can substitute in that formula to find the E naught. By using that value, we have calculated the voltage regulation. So the formula to find the voltage regulation is the same, E naught minus V divided by V into 100. How we are obtaining this E naught? So that is entirely different from methods to method. In the last session, we have discussed about the EMF method. So that the EMF method is called as the pessimistic method. So you can look at this slide. Here we are telling that the EMF method is the pessimistic method. We know that optimistic thinking, pessimistic thinking. Pessimistic thinking means he is having more negative thoughts. Like that we will feel. So here the EMF method gives the regulation value which is higher than the actual value. So that the EMF method giving the information about our machine is pessimistic information. If the voltage regulation, actually the voltage regulation value is maybe 5 or 6%, but by using that EMF method calculation, it shows that the value is more than 15 or 16. So it will create the negative impact on that machine, so that it is called as pessimistic. Next, now we are going to see about the MMF method. In this MMF method, the voltage regulation whatever we are calculating from this, which is lower than the actual value. In the previous case, it is higher than the actual value. In this case, it is lower than the actual value. So that it is called as optimistic method. So what is the difference between these two? In the EMF method, it gives the voltage regulation which is greater than the actual value, but in the MMF method, it gives the voltage regulation which is lesser than the actual value, so that it is called as optimistic method. Normally, if we have any issues in our health, if anybody is consoling us who don't have anything, it will be all right within few days. So he is giving a positive energy for us. So like that, here the MMF method gives the voltage regulation which is lesser than the actual value, so that it is called as the optimistic method. Okay, everything is okay, but technically, what is the difference between these two methods in the calculation procedure? How we are calculating it? So in the EMF method, the armature reaction effect is substituted by an additional armature reactance. So armature reaction effect, the effect which is due to the armature reaction, is considered as the additional armature reactance, or we are considering here that as one parameter, armature reactance. So the combination of the leakage reactance and this armature reactance will give us the synchronous reactance value in the MMF method. Okay, in the MMF method. But sorry, in the EMF method. In the EMF method alone, we are calculating the synchronous reactance. But in the MMF method, the leakage reactance of the armature, the leakage reactance which is present in the armature is substituted by an additional armature reaction effect. So vice versa, in the first case, the reaction effect is considered as the reactance, but in this case, the leakage reactance is considered as the armature reaction effect. So that, in the other words, it is assumed that the change in terminal potential drop on the load is due to entirely the armature reaction. Okay, so it is the technical difference between the EMF method and the MMF method, how we are calculating these two. So to calculate the voltage regulation by this MMF method, we need the same test data, no load test or OCC, open circuit characteristics test, OCC test. We don't call it as OCC, OC test and AC test. Okay, so OC test and AC test. Wait a minute. OC test and AC test. But here apart from these two tests, we require the RA value also. Okay, additionally, we need the armature resistance values. So these are the test data required for this, but here I think the RA value is not required. From the OC test, it is similar to the previous case. I will show you the diagram once again. Yes, here it is our alternator's stator part. It is our rotor part. It is the prime mover. So by using the prime mover, we are giving the mechanical energy to the alternator. The alternator delivers the electrical power or electrical energy. Okay. Here the output of the alternator is kept at open. The terminals are kept at open. By varying this field rheostat, we will be getting the different excitation current, that is the field current value. Then here we are getting the open circuit voltage. The voltmeter is connected between the two phase wires, so it will give you the line voltage at the open circuit, VOC line to line value. So here we will be getting the field current. By using these two, we can draw the OCC graph, the field current versus the V0 per phase. Then to conduct the short circuit test, by using a low resistive wire, we have shorted all these three wires. Here, by adjusting this field rheostat, we will be bringing the current of the armature to its rated value, or 125% of its full load value. Okay. So the prime mover is always connected with this. We will giving the mechanical power, then only it will produce electrical power. There is no change in that. Here, by varying this, we will be getting the two current values. One is the field current, another one is the short circuit current. So we are going to draw the graph between field current and the short circuit current. Okay, right. Yes. So from the OC test, we have, by using that values, that is the field current in the x-axis, open circuit voltage in the y-axis, we have drawn the graph. We have drawn the graph. So that is the OCC graph. Okay. Then from the short circuit test data, we have drawn the short circuit graph. Now, by using this MMF method, I am going to choose the two field current. The field current 1 and the field current 2. What is this field current 1? What is this field current 2? The field current 1 is the field excitation that is required to generate the rated open circuit voltage. So it is OA. From O to the A is the field current which is required to produce the rated armature voltage, open circuit voltage. Second one, IF2. So the field current OC up to this. The field current required to circulate the rated short circuit current. So there are two field current data is required here. One is OA, another one is OC. Okay. By using these two values, either we can draw the phasor or we can use the formula. There are two ways. I am going to explain you by using the formula how to calculate the resultant field current which is required to know the open circuit voltage. Okay. So here we have calculated these two values. The first one, the IF1, is the field current required to produce the rated voltage. Second, IF2, it is the field current required to circulate the rated short circuit current. So by using these two values, we will find the total field current requirement. IF1 square plus IF2 square plus 2 IF1 IF2 cos of 180 minus 90 plus pi. Whether we are going to use plus or minus here, it is based on the type of load. If it is lagging power factor load, here it is positive. For the leading power factor load, it is negative. For the unity power factor, we don't have the angle difference. We are going to calculate from IF1 and IF2. So by using this formula, we can calculate the total field current requirement. Okay. Then after calculating that IF value, here it is 90 plus pi. Okay. So the angle, for example, if you are calculating it for the power factor of 0.8 lagging, so that cos inverse of 0.8, it will give us the value of 36.86 degree. For the 36.86 degree, we are adding here 90 plus 36, it is around 126 points something. So it is our resultant value. So if you draw the curve from this, it is our total or the resultant field current. Now it is our E0 value for the IFR or IF total field current. So it is our E naught. By using this E naught, we can calculate the regulation. Okay, so let us go to the next method, that is the ZPF method. We will move to the next method. So before going to that method, we can see a simple problem based on this. So here they have given the data. They have conducted the OC and SC test for the 3-phase star connector, 1000 kVA. It is a power rating, 2000 volt voltage rating, 50 Hz frequency. For the synchronous generator, they have given the values. The field current, it is the field current in amperes. By varying the field current, they have noted the ammeter values. Open circuit voltage, OCC value. Then the short circuit current, they have taken at 3 different stages. Okay, so here the armature resistance value is 0.2 per phase. Then they are asking us to draw the characteristics curve and find the percentage of regulation for the 0.8 and 0.8 lagging and 0.2 leading. Okay, so these are the given data: power rating, voltage rating, armature resistance. We are going to calculate the voltage regulation at 0.8 power factor lagging and leading. The required formula to find the E naught value is the IFR. IFR is the resultant field current. So here you can write plus or minus. If it is plus for the lagging, minus for the leading. Okay. First we are calculating the full load current by using the power and the voltage. We have calculated the value. Then all the open circuit values are line quantities. So convert it into phase values. So we can convert that values. By using this per phase voltages, we will be drawing the graph. It is our OCC graph. So it is our OCC graph. Okay. Then I have drawn the short circuit curve also. So as per this, what is the IF1 value and IF2 value. So to accurately calculate the open circuit voltage per phase, we will be calculating the rated voltage plus IARA cos phi. This IARA drop is also added here. So the rated voltage is 1201 volt. For that voltage, what is our field current? I have obtained this value from the previous graph. Okay. So for this graph, what is my field current? IF1 32.5. Similarly, for producing the 288.6, it is the full load current. For that, the required field current is 29 ampere. 29 ampere. Okay. So if you are substituting all these values here, you will be getting the IFR resultant field current value is 55.02. For that 55.04, what is our open circuit voltage? So we are obtaining this from the graph. Okay. So it is our E naught value. So by V divided by V, we will be getting the voltage regulation. So 1550 open circuit voltage per phase. So open circuit voltage per phase is for the 2000 ampere, it is our open circuit current value. Sorry, wait a minute. 2000 volt, 2000 divided by root 3, 1154. Yes. So for that 1154, if you are substituting in this you will be getting the regulation for the lagging power factor. Similarly, I am calculating it for the leading power factor. In the previous formula, I am going to add a simple change. Here I am going to substitute minus instead of plus. That's all. If you are substituting minus here, you will be getting the E naught value which is less than the full load voltage, so that the percentage of regulation for the leading power factor is minus 5.63. Okay, so it is the so next I will move to the next method, zero power factor method. So what is meant by zero power factor method? So here additionally with the no load under the blocked rotor, I need one more method, zero power factor test data, that is also required here. Okay, so in the zero power factor method, it is also called as the Portier method. The synchronous impedance method, the armature reaction effect is substituted as a armature reaction. In the MMF method, the leakage reactance XL is considered as a armature reaction. But in the zero power factor method, the voltage drop due to the armature leakage reactance and the effect of armature reaction are taken into account separately. So initially the armature leakage reactance is considered as a armature reactance. In the ampere turn method, the leakage reactance is considered as the armature reaction effect. But in the zero power factor method, leakage reactance and the armature reaction effects are taken into account separately, so that we will be getting the voltage regulation value which is near to the actual value. Hence, it gives the more accurate result. Okay. So here, in addition to the OCC test and the short circuit test, I required the ZPF test value also. Zero power factor lagging load characteristics. Zero power factor lagging means we required a pure inductive load. Okay. Then the effective resistance per phase of the armature winding, RA. So it is, we have already calculated this value and this and the RA value for both EMF and the MMF method. Okay, but now we need the additional test data from the zero power factor test. Okay, yes. So from these three tests, we have taken all the values. First one, here also we are taking the field current in the x-axis, open circuit voltage in the y-axis, and the short circuit current. In the y coordinate, we are choosing the two values. In the x, we are choosing only the field current alone. Okay, right. So here I have drawn the graph of OCC from the OC test. Then I have calculated I have conducted the zero power factor test. At this zero power factor test, at the rated voltage, I will adjust it. I will bring the field excitation to produce the rated current and the rated voltage at zero power factor. Okay, so I have taken that value also. This point C is taken from the short circuit test. IF is the field current which is required to produce the rated short circuit current. So that point is taken here. Then it is the field current required to circulate the rated current at the rated voltage at a zero power factor. By using these 2 points, I am drawing the curve. It is called as zero power factor full load curve. Okay, I have drawn the graph also. Now, wait a minute, I will erase everything. Okay, so I have drawn this. Now I am going to draw the tangent for this OCC graph. This tangent is called as the air gap line. Then I will draw the horizontal line from the point S. The length of this S and Q must be equal to this O and C. For example, if here I am choosing the graph, for example, if I am getting 2 centimeter here, I will be going to draw this for the 2 centimeter. Then I will draw the parallel line from this tangent. I will just move the point from the tangent. It intersects my OC curve at some point. So I have drawn this line. Okay, it is the spacing. I have drawn this. Now I will join these 2 points P and S. I will be getting a triangle. From the P, I will be drawing a vertical line. So I will get a right angle triangle from this. So it is called as the Portier triangle. Okay. So in this IF2, wait a minute. IF2 is the field current required to overcome the armature leakage reactance. This PR is the drop due to the armature reactance. So combination of I into XS or IQ. Okay. So from this OCC graph, I have drawn the triangle. I can draw this Portier triangle at any point from this C to S. At whatever may be the point, I will be getting the same answers. So now you can look at this. I am getting the following information, or I am gathering the following information from the Portier triangle. The length of PR. What is this length of PR from these 2 points, the vertical line? It represents the armature leakage reactance drop. the length of RS, this RS represents the field current which is required to overcome the demagnetizing effect of armature reactance. RS is the IF2. It is the field current required to overcome the demagnetizing or armature reaction effect, to overcome the armature reaction effect, because it is the zero power factor lagging test. So if it is the lagging power factor, definitely the armature reaction effect is the demagnetizing effect. From this demagnetizing effect, to overcome it, we require the additional field excitation, or we need additional magnetomotive force. The number of turns is always constant. By varying that, by changing the field current, we will be getting the different magnetomotive force. So it is the field current required to overcome the demagnetizing effect. Then QR or RQ, which represents the field current necessary to balance the armature leakage reactance drop. It is required for demagnetizing effect. This QR is required to balance the leakage reactance drop. So the Portier triangle is same for the given armature current, and hence it can be transferred anywhere to fit between the two characteristics. You can draw this Portier triangle at anywhere else. You can draw here, or you can draw here, or you can draw anywhere else. So from this Portier triangle, we can calculate the voltage regulation. So how we will be calculating the voltage regulation? Yes. So voltage phasor is taken as the reference. IA lags behind your voltage. This IARA drop is drawn parallel to this IA phasor. It is the IA into XL, leakage reactance drop. Okay, where it is exactly, I will be drawing at 90 degree perpendicularly. From this point to here, if I am joining, it is E. Then if I am considering the armature reaction effect, then it is our E0 value. Here the IF is drawn 90 degree for your E0. IF1 is drawn at 90 degree for E. If you add these two, you will be getting the IF2. This IF2 is parallel, or it is 90 plus theta. Theta is our lagging angle. Okay. So by using this, I can calculate the voltage regulation E0 minus V by V. So how I am calculating the voltage regulation from this? Okay. So it is the data which is given for the zero power factor test. So a 11 kV alternator, 1000 kVA 3-phase is connected with the alternator, has the resistance of 2 ohms per phase. The open circuit and the full load zero power factor characteristics are given below. These two are the data obtained from the OCC test. It is the zero power factor test data. Find the voltage regulation of an alternator for the full load current of 0.8 power factor lagging by using a Portier method. Okay, as usual, first these are all the line voltages. Convert these values by √3. Divide all these values by √3. You will be getting the per phase voltage. First we will be doing that for the OCC as well as for the zero power factor test. All these values are divided by √3. First I am dividing all these values by √3. Then I am getting the per phase quantity, per phase voltage. Okay. Then I have drawn the OCC graph. In the x-axis I am choosing the field current. In the y-axis I am choosing the, here it is the data obtained from the short circuit test. Here they have not given the short circuit test. All these data are taken from the zero power factor test values. Okay, so we have drawn the zero power factor graph. Then it is 2 centimeter. For the 2 centimeter I have drawn at the rated voltage. rated voltage is given in your problem. Then I have drawn the air gap line. For that air gap line, I have drawn the parallel line which intersects my OCC at some point. From that point, I have drawn the vertical line. Then the right angle triangle under this triangle is created. It is called as the Portier triangle. Okay. So from this Portier triangle, wait a minute, I will erase the unwanted portions. Okay. So here this RS value and the PR value is measured and it is calculated. So by using these two values, first I have calculated the full load current and the per phase voltage. It is my rated voltage. The PR value is 1200. It is considered as the IA into XL. Instead of this, in this formula, instead of IA into XL, I can substitute that value. Then the voltage is 6350. The power factor calculated it for 0.8 power factor lagging. Then the IA value is 52.5. It is multiplied with the RA 2 ohms. Similarly, B I cos sin pi value. Substitute all this, you will be getting the 7210 voltage. In the alternator for this, what is our required field current? Required field current is 108 amperes. It is our E naught. Okay. By using that, from that RS value 26 amps and the field current required to produce the rated voltage is 108. By using this, I am calculating the IFR. From that IFR, I am getting the resultant current. By using this data in that graph, I am calculating the EMF corresponds to this field current. So it is 7650. 7650 minus 6350. I will be getting the voltage regulation as 20.47. Okay. So I will come to the first slide once again. Yes, you can look at this. We have calculated the voltage regulation for the different power factors. Okay. So there are three methods. One is the synchronous impedance method. Another one is the synchronous impedance method. Another one is the ampere turn method. Next one is the ZPF method. In first, it is called as the pessimistic method. Ampere turns method is called as the optimistic method. It is the accurate method. So I have calculated all the values. By using all these, I can able to find the voltage regulation by using these three indirect methods: synchronous impedance method, ampere turns method, and ZPF method. Among these three, in the synchronous impedance method, first I am calculating the ZS. In the MMF method, I am calculating the IFR. In the zero power factor test, I am drawing we can draw the Portier triangle. So among these three methods, the accurate method is the ZPF method, but the procedure and the calculation methodologies are somewhat tedious compared with the first two methods. So in the first, we are calculating only the ZS. From the ZS, we are finding the X suffix S value. Okay. Then in the ampere turns method, we need the IF1 and IF2 value, resultant field current. By using these two, IF1 and IF2, we are calculating the resultant field current. From the resultant field current, by using that resultant field current, we can project it in the graph. We are getting the open circuit voltage. Then in the ZPF method, we require the three test data: OCC, short circuit test, and the ZPF test data. By using these three test data, we can draw the graph for the OCC and the ZPF curve. By using this data, I can draw the Portier triangle. By using that Portier triangle, I can segregate the leakage reactance drop and armature reaction effect separately. By using this, I can calculate the IFR. From the IFR, I can get the E0 value. Okay, right. So by using this, we can get the values. These are the three indirect methods. Okay, thank you.